Hey there, it's Miss B, and we are looking at the Unit 5 Lesson 2 practice problems, and this is for Illustrative Math Algebra 1. So let's dive in. We have a first question here. We have a population of ants that it starts at 10,000 at the start of April, and since then it triples each month. So let's complete this table. So if it is month since April and that month is 0, the number of ants is our starting amount. So that's going to be our initial value, or 10,000. Okay. And since then, it's going to triple each month. So we're going to multiply it by 3. Definitely use a calculator for this assignment if you want to. I suggest it. I'm going to use a calculator just to make sure that I'm actually doing all of this correctly. So if we take 10,000 and we multiply it by 3, that first one, probably pretty easy. We're going to get 30,000. Oops, that's an eraser. 30,000. Okay. And then if we multiply that by 3 again, we are going to get 90,000. Well, let's multiply that by 3 again. And this is actually going to give us 270,000. And if we multiply by 3 one last time, we will get 810,000. Okay, so that was part A, was just to complete our table. So what do you notice about the population differences from month to month? I'm going to say it is growing by a larger amount each time. Meaning that in the first place, it only grew by 20,000, but then it grows by 60,000 between these two. And it's gonna grow even more as it keeps going. So part C to this says, if there are n ants in 1 month, how many ants will there be a month after? So it's just asking us to explain using algebra what our process is each month. So I was multiplying by 3, so I'm going to take n and multiply it by 3. Now you can write that as 3n, or you could write it as 3 times n, or you could take n times 3. But I prefer 3n because this is normally how we'll deal with these numbers in equations. And that's it for question 1. Let's move on to question 2. We have a swimming pool containing 500 gallons of water. A hose is going to be turned on and it will fill the swimming pool at a rate of 24 gallons per minute. So that seems important. We also had 500 gallons in there. Which expression represents the amount of water in the pool in gallons after 8 minutes? So this is actually going to represent a linear function because I am not going to use exponents. I am just going to use the 500, and then I'm adding 24 gallons for every 8 minutes. So I'm not going to add 24 and then add 8. That wouldn't make sense. I'm not going to add the 8 minutes. But I am adding, so when this one right here, actually my first option, doesn't have adding at all. It has everything being multiplied. So it is not going to be this one. There's no addition in there whatsoever. My second one has only addition, but I shouldn't be adding the 8 minutes. 8 minutes tells me how many times I'm going to be adding the 24. So it's not going to be this one either. And the very bottom one actually only has multiplication and exponents in it, so it's not going to be that either. We're going to pick choice C because that says I am going to add 24 to this 8 times. So this says, and I'll write it out, 500, and then add 24 8 times. And that is what it's showing. It's saying, hey, we're adding 24 gallons, and then that is going to happen 8 different times at our 8 different minutes. So we're going to choose choice C. We have another question down here, number 3. So the population of a city is 100,000, and it's going to double each decade for 5 decades. So I have a starting amount at 100,000. I also am seeing that it doubles. So I know that doubles means times 2. And then a decade is 10 years. And then it's going to be 5 decades. So we don't need to know that a decade is 10 years because we actually are just expressing this in decades. But we're going to select all expressions that represent the population after 5 decades. So if we're doubling repeatedly, that is actually going to be multiplying. So unlike the previous one where we were adding stuff multiple times, we're multiplying a bunch here. So the first thing I see is that option C is correct, but there are multiple correct answers here. But this takes my 100,000 and says, oh, it's going to double. And that's 1 decade, and then 2 decades, and 3 decades, and 4 decades, and 5 decades. So it is going to double those 5 different times. Now, it's not shrinking, so I'm not going to have 32,000. That wouldn't make sense because that would mean my population is shrinking. And it's not going to be 300,000, 320,000 either, because when we double, we'll get 200,000, and we'll double again and get 400,000. So we're easily going to pass that one up. So now we're just going to look at our representations down here using exponents. Since I know that it's 2's being multiplied with each other 5 times, I'm actually going to choose choice E because the 5 tells me how many times. Whoops, I guess someone's at my front door if you heard that in the background. But the 5 tells me how many times to actually multiply this 2 with itself. So D would actually mean 100,000. And then we would multiply it by 5 and then multiply it by 5. And so that's not the case for that. Okay, so let's move on to the back. These are the last 3 questions here, so this is the last page. So let's work through them. We have a table showing height in centimeters of the water in a swimming pool at different times since the pool has started to be filled. And now they're asking, does the height increase by the same amount each minute? And explain how we know. And then does it increase by the same factor? And explain how we know. So let's actually look at this and look at how we can tell what it's changing by each minute. So this is just like analyzing slope. If you've done that before, this is 1 minute that's gone by here. And right here, we have 0.5 in height. This next step is 1 minute. And again, it looks like we have 0.5 in height. And we have 1 minute. And again, 0.5. So yes, it increases by 0.5 each minute. And then if you weren't sure, you can actually subtract these. I was just kind of doing some quick subtraction, I guess, in my head. You can kind of see that we only added 0.5 on here. And so really, if these were numbers that you didn't know, you could just subtract them in order to figure out the difference between them. And you would take this one and then subtract the one that's above it. not the other way around, because if we did it the other way around, you'd get a negative 0.5. So we'll say you can subtract the heights and minutes to compare. Other than just saying, I looked at the table. Okay, so now we want to look at the factor. The factor means what are you multiplying by? So a factor is what it is multiplied by. And you're pretty much never going to have a common difference like this one. The difference here is being 0.5 in 1 minute, and a common factor at the same time. So we should not be increasing by the same factor each minute. We can check this by dividing. So we can say, instead of these being subtracted, we can say 150.5 divided by 150, and then 151.5 divided by 151. So I'll actually write those out, and then I'll punch them in a calculator and show you guys what I mean. So we can say 150.5 divided by 150, and then we're also going to say 151.5 divided by 150, and my calculator is going to show me the answer in just a second here. So 150.5, and we're going to divide that by 150. Calculator says this is 1.00, so 1.003333, and the threes keep repeating. Now, if I do 151.5 and divide that by 151, I actually get a different number. I'm going to get a close number, 1.003311258, and that's as far as my calculator goes. So this is not equal to. So no, I checked by dividing. The heights. Now, if you checked by the minutes, we're still just looking at how that's changing and doing subtraction with those, since it's the input, but the height is what we would be checking, or our output is what we would be checking to see if it was being multiplied or divided each time. Okay, so that's question 4. Let's look at question 5. We have bank account C starts with $10 and doubles each week. I know that doubling is times 2. I also have $10. And bank account D is going to start with 1,000, and it's going to grow by 500. I'm going to say that's like adding 500, is what we're going to interpret that as. So when will account C contain more money than account D? So let's actually just do some guess and check. We know eventually it'll pass it up, because anytime we're multiplying, it's going to pass it up. But account C. All right, now you can't see me actually plugging these things in my calculator, but I am going to start with my $10 and multiply by 2. So I can actually make, like, I'll make a little table. I'll say like week. I'm going to make a horizontal table. Actually, I know I'm trying to make a vertical one right now. So I'm going to say the week number. And then I am also going to say what's in C and what's in D. So let's see if I can make a box here and if it'll play nice with me. Not quite. That's okay. Nope. Draw a better one. Well, I at least want dividing lines between these, so I'll just make some horizontal lines here. Okay, so we're going to start with week 0. That's our starting balance. Bank account C, I might run out of room, is $10, and D is 1,000. Okay, so C is going to double, so if we multiply that by 2, the next week we are going to have $20. And the next week after that, we're going to have $40. And the next week after that, we're going to have $80. And the next week after that, and we're going to keep going. So this will be 160. I'm really just looking to check and see how long it's going to take me to pass up 1,000 and potentially even 2 or 3,000. So at the 1,000 mark, that's where I'm going to start plugging in numbers for D, and we're going to see then from there kind of each week how it goes. So the next week, if we had 160, when we double that, we're going to have 320. Doubling that number would give us 640. And then when we double that one here, we would have, I believe 1,280, but I'm going to double check myself on that because, yep, 1,280. Okay, so here is where we might start catching up. And then we'll actually look at account D. So 6 and 7. So 1,000, if I am adding $500 each week, I'm going to have 1,500. And then I will have 2,000. And then I will have 2,500. And then 3,000. Okay, well, this one's growing pretty fast, but still. 3,500. And then 4,000. And 4,500. But at this point, my bank account for my other one is going to be growing pretty fast. Because once I have 1,280 here, so 1,280, when we multiply that by 2, we're really going to start to catch up. We're going to have 2,560. So we're still not caught up yet because this is now at 5,000. We're getting closer. I'm going to extend my table a little bit here. I didn't know how long I was going to need, but apparently longer than I thought. So now 2,560, if we double that, we get 5,120. Okay, so I've almost caught up, but this one is going to be 5,500. And that's after 9 weeks. So on the 10th week, when we double what's in bank C or in account C, that is going to actually reach over 10,000. So we are going to say 5,120 times 2, and we will get 10,240. So 10240. And this account here, we're going to have $6,000. So I would say here at week 10, and my reasoning is going to be my chart. I made a table. To compare. And yeah, so that's my reasoning is I just, decided I would make a table and just literally show. If you knew it would be at a certain point, you can absolutely describe what your reasoning is. But if you're just making a guess, you should actually be checking your numbers. Okay, and question 6, and I think this is the last one, it just has 3 parts. Suppose C is a rule that takes time as the input. Okay, they're just telling me I have time as the input. Oh, and it gives the class on Monday as the output. And they're giving us, for an example, the actual time on the clock, so C of 10:15 equals biology. So let's say, what if we had a class at, well, my first period class starts at 8:30, so I'm going to say C at 8:30. And we can say that is algebra. Now we know C at 10:15 is biology, so for us, that's normally in the middle of second period. So third period, maybe I say C of this. We start, let's just use noon, because I know noon is in the middle of that class. So let's use C of 12. That would be third period class, so maybe that's academic support. I'm just giving examples. Again, you can use kind of whatever class, maybe whatever your schedule is like. And then for fourth period, I'm going to say C of, and what's the time that I know? I know 2 o'clock is right in the middle of fourth period, so I'm going to choose 2 o'clock. And that we can say is, maybe this is like PE. Sure. Okay. So does each input to C have exactly one output? And explain how you know. Well, when the input is time, the output is the class. And we're going to say it's the class you would be in on Monday. So I'm pretty sure it's physically impossible for you to be in 2 different places at the same time, meaning you shouldn't have 2 classes at the same time. You might have it on your A and B schedule, but it's specifically your class for Monday. So exactly one output, yes. And we're going to say you can't be in 2 classes at the same time. And explain why C is a function. Well, the definition of a function is that each input has exactly one output. So we're going to say because, exactly that. So because each input only has one output. And that is it. So that's the end of this homework assignment. Thank you for joining me for this video. Again, this was the Unit 5, Lesson 2, Practice Problems, and this is Illustrative Math Algebra 1.